Our final type of quadratic word problems are called optimization problems. Because parabolas have a vertex point that's either a max or a min, and a lot of things in the world follow a quadratic model, these are very useful in worlds of business, accounting, and financial situations. So we say we have this last year's yearbook, cost them $75, and 500 were sold. They did a survey that said that if they were to reduce the price by $5, 100 more students would have bought yearbooks. The problem is, if you can't just go all the way down to zero, everyone have a yearbook, but you still have to make money. So they need to know what price should be charged to maximize the revenue from our yearbook sales. So with an optimization problems, we really have two equations that we're trying to build every single time. One's about the money. Actually, we want to call it profit. Or no. One's about profit. I lied. I want to go back to the money. And the other one is about number sold. We are then going to put both of these together for our profit equation. That's why I wanted to change it. So profit is how many you sold times the price that you sold it at. So here's where the money part comes in, and here's where the number of sold comes in. So last year, their profit, P, was equal to 500 times 75. This was last year's setup. After their survey, they figured out that if they reduced the price by $5, 100 more students would buy yearbooks. So we're going to add in a new variable x, and x is going to be the number of times they change the price. So they can change it one time, they can change it two times. So we could do this by guessing and checking. Like we could go, alright, we've reduced it down to $70, which means 600 people. We could figure out the profit. We reduced it another $5, so it's 65, and now there's 700, 60, 800. And we could check each one of these models. We don't want to spend the time checking each individual model like that. So instead we set up an overall equation. The profit is going to be equal to the initial 500 plus 100 students for every time they reduce. So if they reduce it once, they get 100 students. They reduce it twice, they get 200, 300, 400, so on and so forth. On the same turn, the price is going to reduce $5 every time they reduce. Like so. What we're going to do is now we're going to FOIL this. So 500 times 75 gives us 37,500. In the middle we end up getting plus 7,500 x. Then outer we get 500 times 50, or times 5, not times 50, times 5. Gives us a negative 2,500. And 5 times 100 gives us negative 500 x squared, all equal to our profit. I'm going to rewrite this. Profit is equal to negative 500 x squared. Combine my terms in the middle, it gives me positive 5,000x plus 37,500 One too many zeros there. Alright, so we have this, and our next thought might be, alright, we're going to set it equals 0 and find our roots. We're not finding roots. Because I don't want to know when my profit's 0. I want to know when my profit is maximized. So we're looking for max profit, which means we're looking for the vertex. So x is equal to negative b over 2a. So we get negative 5,000 over negative 1,000, which means we get 5. So x equals 5 means they need to reduce the price 5 times, or by $25. Let's make sure we answered our original question. What price should they charge? They should charge $50 for each year to maximize their profit. Let's try another optimization problem. So an auditorium can sit 600 people at $10. If they increase the price by $1, 50 less people will come to the show. Which price maximizes the profit? Right? It's the same thing. We've got the money side of the equation, and we've got the capacity. That's what I'm looking for. So again, their profit is going to be equal to their money times their capacity. So originally it was $10 times 600 people. They're going to increase their price by $1, but you're going to lose 50 people each time. So again, we're going to have 10 plus x. There would be that $1 in front, but we don't really need to put the 1. And then every time they do that, they're going to lose 50 people. So again, we FOIL to get our profit. I'm going to put it over here. Is equal to 6,000 minus 500x plus 600x minus 50x squared. I'm going to rewrite this. Negative 50x squared plus 100x plus 6,000. So what's cool is this number right here in both the last two examples, 6,000, was their original profit. So 6,000 was their original profit. We're just trying to have it add with a positive number here. You can see that if our first term gets to be the largest, it's actually going to subtract from negative 6,000. So there's a perfect sweet spot where we're gaining more money than the original profit, but then there's a point where it would tip over and we start losing money again, just like you'd see in the parabola. So we might see 6,000 perfectly right here on either side, and then a certain amount will bring you the max, and then after that a certain number will start bringing you back down. Once again, we're looking for the maximum, so we're looking for the vertex. X is equal to negative b all over 2a. Gives us negative 100 over 100, negative 100, meaning 1. They should increase the price by $1 single dollar. Just once. So the price they should charge should be $11. This also works with a area problem. You want to construct a rectangular playground, dokie dokie, you have 500 a 500-foot roll, so 500 feet of fencing in this field. So the whole perimeter can only equal 500, meaning 500 has to equal the two lengths and the two widths. So we have no idea what the length is going to be, we have no idea what the width is going to be, but we know that put them all together it could be no more than 500 because that's all we have. So this is where we're going to do some substitution. We're going to solve this either for L or for W. First thing I'm going to do is divide everybody by 2. Gives me 250 is equal to L plus W. Let's solve for L. And we get that L is really equal to 250 minus W. We want to maximize the area, so we're going to use our area formula. So area is equal to 250 minus W times W. Distribute the W. I'm going to rewrite it here, and we get negative W squared plus 250 W. Again, I have no idea about the area. We're not trying to find the roots. We're finding the vertex. We have everything we need for the vertex. We have B and A. So that's what we're going to do. X is equal to negative B all over 2A. In this case, actually, it's not going to be X. It would be W, because that's our variable. We get negative 250 over negative 2 equals, so of course it does, that's why it's over there. Come on, Carla, get it together. The negatives cancel out, we get 125 for W. So the width has to be 125, which means the length has to be 125. Which means the best way to maximize the area of this rectangular playground is to make it a square. I think I got one more. Rectangular field. It's going to be used on all four sides. There will be a line of fence across the field, parallel to the shorter side. If 900 meters of fence are available, what dimensions of the field produce the maximum area? Alright? So this one we have a rectangular field. And we're thinking, oh, it's going to be a square like the last one. The problem is this one, we have an additional fence right down the middle that's parallel to the shorter sides. So meaning we have the entire lengths and we have 3 widths. That means 900 has to equal 2 lengths plus 3 widths. We're going to do, once again, some substitution. To me, I'd rather have everything divided by 2 rather than everything divided by 3, because divided by 3 you have a lot of repeating decimals. So I'm going to subtract 3W. That gives me 900 minus 3W equals 2L. Divide everything by 2. And so L is equal to 450 minus 3 halves W. We want to find the area of this maximum field. So it's still length times width. It doesn't change anything. Length times width, because we're trying to find the area of the entire field. So area is equal to 450 minus 3 halves W times W, which means we have negative 3 halves W squared plus 450 W. Find our vertex. W is equal to negative B all over 2A. So we get negative 450 all over negative 3. Because the 2 here cancels with the 2 here, just leaving us that. So W needs to be 150 feet. So W is 150, 150, 150. So that's, we want to find the dimensions. So we know what W is. Length is equal to this equation. So I'm going to take 3 times 150. Oops. We don't want it to be that large. 450. Divide that by 2. So the lengths are going to be 225 feet long. That answers our first question. What are the dimensions? Final question, what is the area? So we're going to multiply those two numbers together. So 225 times 150. 33,750 square feet of area.